Hi everyone, I'm Diana, and today we're going to be talking about the exciting potential of reinforcement learning. Okay, the plan for today's talk is as follows. We're going to start with a bit of history and hopefully draw some motivation and inspiration for artificial intelligence-driven future. We will then introduce reinforcement learning as a way of modeling and thinking about general AI problems. After which I will highlight what I believe to be some of the most challenging problems we face as a field that we would need to address and at least improve on in order to scale up even further and increase the applicability of these algorithms, as well as maybe current methods and recent progress that we've made in these directions. Finally, I'm going to end on a note on the current applicability of these methods and their potential future applicability. Okay, let's dig into it. So let's start with a bit of history. Actually, the history of automation. Looking just a few centuries into the past, mid-18th century marks the beginning of the Industrial Revolution, the age of the machine, which transformed forever the landscape of industries, urban and rural areas alike. But what was so special about this era? I think the emerging theme here is the automation of physical solutions. With the invention of the steam engine, the internal combustion engine, and the use of other energy resources, all of these enables us to go beyond our physical limitation, the physical limitations of how much a human can carry, how much it can travel in a particular period of time without getting tired, and so on. Many more technological advances later, large segments of the industry were completely or almost completely mechanized by the early and mid-19th century. This allowed us to increase our production in many material, food, and goods with small or very, very little human energy expenditures. All of these enhance our natural physical abilities by automating some of the tedious processes, manual processes that we would have had to do or undertake ourselves otherwise. Then we got even more smarter. We realized we can do the same thing with mental processes, like basic computations, additions of numbers, and so on. As long as we can describe to a computer, step by step, corner case by corner case, what to compute, how to execute it, we could outsource the whole computation to the external process. Central to this revolution was the mass production and the widespread of digital circuits and derived technologies like the computer, the cell phone, and of course the internet. As the years progressed, the computation feasibles on these devices grew more and more impressive, grew faster and more inexpensive. So did the scalability of the recipes or the algorithms that we could program in. So you can see maybe a clear pattern here. We gradually outsource some of our work, manual or mental, to a different system that was far more efficient in executing these prescribed solutions, thus enhancing our natural capabilities in these dimensions. Now, I would argue that the new frontier in this automating process is automating the process of finding these solutions. All the progress that we've seen so far has been in automating known solutions, prescribed recipes. Now, the new frontier here is automating the finding of this solution, the finding of this algorithm, the sequence of actions, mentally or manual, to be executed to achieve a particular goal. And this is I think, the promise of artificial intelligence and maybe its ultimate test. Okay. To be more precise in this desiderata, we would really want a system where we can specify a goal or a task, and the system will come up with a solution on its own. More precisely, the system will learn solutions from given data. This can be things like pattern recognition, imitation, generalization, automation of human tasks. And the second part, which is probably one of the most understated and underdeveloped problems in whole machine learning, is learning to find the relevant data. And this is what we call in reinforcement learning the exploration problem. Okay. So this motivates me to pitch to you reinforcement learning as a framework to think about addressing this desiderata. And I'm going to introduce the reinforcement learning problem as the problem of sequential optimal decision-making that can have long-term consequences into the environment and potentially has sparse, incomplete feedback. Note that reinforcement learning formalizes the problem, not a particular solution. It provides us with a framework to think about acting into the world, a framework about learning how to act into the world. Now, this sequential decision-making problem often entails actively reasoning and trading off short and long-term consequences and payoffs. Sometimes we have to pay something in order to get something at the end. We have to invest energy or incur costs in order to achieve a better payoff further down the line. What makes the problem a lot more complicated is that usually in reinforcement learning, we assume that the world is unknown and everything is unknown. The world around us, the environment, the interactions with the environment, the outcomes of those interactions, the reward structure is unknown many times. The feedback that is given by the environment is often very sparse, sometimes delayed. And we have to actively make sense of all of these data, and we have to actively search for information in this unknown world. Okay. Some examples of decision-making problems that we can model in this framework are flying a helicopter, planning a trip, optimizing for time or cost and delay, controlling a power plant, optimizing for relevance or user interaction in web searches, recommendation of products, movies, TVs, managing an investment portfolio, playing a chess, or playing video games. A couple of more examples that are not usually seen as reinforcement learning problems are one-time decision-making problems, usually called bandits, that still have the exploration component in there, but are much simpler reinforcement learning problem because they don't have the sequential nature of the problem. Even something like classification problems, which are supervised learning problems, can be casted as a reinforcement learning problem. Again, it's a very particular class of reinforcement learning problems that don't have the long-term dependency and have this immediate informative feedback via the loss. This is usually the simplest kind of problem that we can have in reinforcement learning. Okay. Now, looking at the overall system, reinforcement learning systems usually have these two components: the agent in the world, and the world provides observations to the agent. This is similar to supervised learning, but we have these two other components mitigating this interaction, which agent can produce and perform actions into the world. And as a result of that, it gets some feedback signal in return. So contrasting that with supervised learning, where we usually have only one stream of data, usually something like observations. This reinforcement learning system has actions and rewards, and the interaction there is a time interaction. Every time an action is taken, we transition to a new state, we get the reward. We take another action, we transition into a new state, and so on. So this is a process that unfolds in time. If you want to map that to something, like supervised learning, you can think something similar to this is something like time series or sequence model that have this sequential structure. But even with respect to those, these two other components, the action, your ability to influence the environment, and the distribution of the things that you're going to see further down the line, and this reward signal are very particular to this. So in most of the supervised learning problems, we have this stream of information, and we need to predict something. We need to answer a question. So what are we predicting in reinforcement learning? Well, actually, it's not a prediction problem at all. The goal of a reinforcement learning problem is to find a policy, a sequence of action that maximizes an expected cumulative return. And this leads us to the reward hypothesis. The reward hypothesis says that any goal or any task that we might want to achieve in the world or solve in the world can be formalized as the outcome of maximizes a cumulative reward. This is a scalar feedback signal that is given to the agent, and is a function of the state and action that is the agent is in right now, and tries to characterize the goodness or the desirability of this state-action pair. Now, this can be, as I said, very sparse and very delayed. For instance, when we're training board games, like something like chess, all of the only reward signal that you get is at the end of the game, whether you lost or won that game. So 0-1 at the end of the game. Anything in between is zero. Like you don't get any feedback in between. So you really have to make sense of all the states and action that you've taken throughout this process, this sequence that led you to a win or loss outcome, in order to learn how you can improve your strategy. Okay. This is just more formally how a return looks like, the cumulative expected return. This is usually discounted by discount factor gamma between 0 and 1. And the expectation of these future returns is what we call value functions. And what we want really is a policy that optimizes for these value functions. Okay. So again, contrasting in terms of problem setting with supervised learning in RL, we're looking for a policy that maximizes the cumulative reward. Usually this will end up being an interplay between prediction problem, policy evaluation problem, where we build this value function and try to assess the goodness of a current policy, and paired with an improvement step based on this prediction. In supervised learning, usually we have a much more well-established prediction problem that is fully supervised. How do we transform this problem into a supervised learning problem? Well, simple. You just have to specify at each point in time, at each state, what is the optimal action to be taken. Maybe you don't need to specify over the whole state space, because we can rely somewhat on generalization as we do in supervised learning. But you have to have this information at least some of the states into the environment. But what if we don't have this optimal policy? Take this example for instance. It's maybe hard to say what the optimal move here is and what the optimal move would be after the next state. Okay, maybe you're not that familiar with the game of Go. Maybe you're more familiar with something like chess or shogi. Even here, it's fairly hard to come up with an optimal play strategy. Here's another example. Even if you consider something like a recommender system, even if this scenario does not have maybe the long-term strategic planning that many of the other games that I've showed requires, this comes with its own unique challenges, like an enormous and structured action space. Like how the action space is the list of things that you can display as recommendations. So all of these examples, we simply do not have the optimal strategy of what to do in order to generalize from that. We just have to learn one. So we really have to go beyond supervised learning, beyond imitating human solutions and just generalizing around them, into a system that really can learn to optimize for this this overall task, this cumulative reward that we specify, which might be user satisfaction or engagement in this particular example. Okay, hopefully by now you got a good idea of what the RL system is and maybe the generality of the complexity that we're trying to address right now. And of course, this comes with new challenges, or as researchers like to call them, exciting research opportunities. Okay. We're going to start with one of them that is, I think it's the one that you encounter more in normal machine learning, which is representation learning, which is function approximation. The premises really is the same, that you have a potentially messy, complex observational space that you want to make sense of. And we have a lot of models and techniques, deep learning models, functional approximator, linear kernels, and otherwise, that can deal with this situation. And the principle remains the same. We just want an embedding of this high-dimensional space that is helpful, that maintains all the information necessary to approximate the quantities of interest. The only thing is the quantity of interest in RL usually are things like policies, value functions, and other long-term predictions about the environment. And this pairing between powerful function approximators and classic learning in reinforcement learning, like temporal difference learning, in this case, Q-learning, has been very successful and has allowed us to scale up these methods to scenarios that were previously prohibited. This is just an instantiation of this, the DQN agent that's, I think, started in part this revolution in pairing this deep learning methods with traditional reinforcement learning methods. And this basically spawned a subfield called deep reinforcement learning that has been very active in the recent years. This is just another instantiation, just a few years back, that shows many of the improvements that we made to this original mechanism, just trying to optimize this interplay between temporal difference learning algorithms and deep neural networks. Okay. The other challenge that I want to spend some time on is exploration. Exploration is the problem of gathering data. The problem is we don't know the world. We don't know what the potentially rewarding states or good outcome are in the world, so we need to find them. We need to both find the good strategy to maximize the expected return, but we need to also allocate some time and resources into exploring the environment. Some of the principles behind RL exploration are random exploration, like naive exploration, where you choose actions randomly around the policy. Another more principle is optimism in the face of uncertainty, where we prefer actions or outcome that have high uncertainty, which for us are a proxy to good learning opportunities. If I'm uncertain about that part of the environment and I go there, there's a good chance that I can refine my understanding of this uncertain area. Another principle is probability matching, and probably the most iconic algorithm there is Thompson sampling, where we're trying to identify always what the best action is, and we're trying to maintain a probability of what the best action would be, and try to sample according to that probability. Now, maybe a more elegant solution to the exploration problem is Bayes adaptive MDPs, where we have particular hypotheses about the world, and we're trying to plan to seek information that will distinguish between these hypotheses. And once we identify in which world we are in, we can do something like model-based RL in order to solve that MDP. Okay. Now, the limitation with all of these strategies, and a lot of the strategies that we proposed throughout the years in reinforcement learning, is that not one of them caters to all of the exploration problems that we care about. A lot of them are good at targeting a particular characteristic of the task, like deadliness, stochasticity, sparsity of reward, the level of stochasticity, the level of regularity that you see in the environment, and so on. But not one of them can cater to all of these characteristics. Thus, a new approach that has seen a lot of traction recently is a diversity-based exploration, where the idea here is that we're going to build a rich collection of behaviors, and we're going to use all of that set of behaviors for exploration. And on top of this diverse set of behavior that will shine in different situations, we would want basically an adaptive mechanism that will choose which of these components are most useful at any point in time. This allows us to adapt both to the task and throughout the training process. Okay? And a particular instantiation of this general principle is Agent 57 that has just been published at ICML this week, where the diversity set of behavior is based on novelty-based intrinsic reward, and different profiles of mixing between external and extrinsic reward and the extrinsic reward, as well as different discount factor that basically put in how much we care about long-term and short-term rewards. And on top of that, of course, is this adaptive mechanism, non-stationary adaptive mechanism that adapts the profile of the usefulness of these behaviors as the training process continues. Okay. And this is the first agent that was able to master all 57 Atari games with superhuman performance. Okay. The last thing that I want to mention is the credit assignment problem. The credit assignment problem is trying to answer the following question. How did past action influence future returns or outcomes? And this is the problem of, given a trajectory with many actions, visiting many states, how do we credit to any of these actions or any of these states? So this is just one path in the environment. Here's another one that the agent took, and at the end of this trajectory, this seems to be a better way of achieving the same final state. But at the end of this trajectory, there was no reward. So what happened there? Well, it turns out that the underlying NDP is something like this, where there are multiple things in the environment that we can interact with, things that we need to avoid, things that we can pick up, like the key. So it turns out that this red trajectory did not go and pick up the key. So at the end, although it reaches the same state, it can't open the chest of treasures, and it gets no reward. Now, the problem with the way we do currently credit assignment is that for every trajectory, whether it was successful or not, we just work backwards in time. So like from the last state, we just work backwards and assessed credit proportionally to the distance it has from the outcome. In this particular example, it means that going around the lake or going around the dancing unicorn is assigned more credit than picking up the key or going around the tree. This is because time is used as a proxy for relevance. So unicorns become more important than keys. Obviously, this points to a more general problem that we are using recency rather than causality in order to do this credit assignment problem. So this is something that people have identified, and a lot of work has been done recently in learning causal models to build an environment, to build a model of the environment, and use this one to do model-based RL. Now, that being said, learning a causal model is non-trivial, especially under open exploration, and model-based learning is not a solved problem. Model-free techniques constantly still outperform these. So there's still a lot more to be done there. Another potential solution here is what we call hindsight credit assignment, which is a work that was published at NeurIPS just last December, where the idea is to look at actions that made the difference. Trying to look at the probability of how relevant the action is to a particular outcome. In this case, the reward that I got at the end of this trajectory. Okay. Now, just to recap some standing challenges that we've explored: representation learning, exploration, more efficient credit assignment. The one that I didn't have time to tackle, but I think it's still very important and will have a lot of traction in the next years, is transfer and the generalization, going beyond the single task. Now to some concluding remarks on the generality of our algorithms versus current applications that we have. So we started with this desiderata of a system that is able to learn solutions from given data and learn to find the relevant data. Of course, a lot of our use cases and a lot of our tests are in simulators and games. but we're trying to adhere to this general principle such that, the same algorithm, the same, solution can be applied to other things like recommender systems, energy saving protocols. We've applied this to cooling data centers, to power battery management. And ultimately, what we would want to contribute to is accelerating science, things like protein folding, mathematics, theory improving, and something like quantum chemistry. Now, in our process to scale these things and apply these things into the real world, there are a couple of unique problems that still need to address outside the conditions that we usually study this, which is simulation or games. One is batch learning and expert and demonstration learning. This is particularly particular to the way machine learning is done these days, with data collection not being part of this process. So I'm not sure if this is something that we need to target right now, or we need to find ways of incorporating exploration into this process and having more active process there. But in order to do that, we need to have safe exploration. Most of our current techniques rely on random or uninformed trials of actions, and systems that are risk sensitive or risk averse need to come into play, and things that are much more sensitive with respect to the amount of exploration that can be done, and having targeted experiments into the world is something that our current exploration techniques do not have. The other thing that I kind of didn't have time to cover is state representation or partial observability, where a lot of the methods that we have right now are relying on a Markov assumption, or are derived with that in mind, which basically means that all of the information that we need in order to make a decision about the future is captured in the current state, which might not be just your current observation. It might be, many observations in the past, and you have to integrate that into an informational state right now that has all the information needed. Okay. And of course, when moving into the real world, we do have to take ethics and our social responsibility and accountability very seriously. This is, I think, particularly important with this technology, where you don't have a particular set of steps. We can't verify every corner case, and probably we won't ever be able to test them. So the potential of malfunction or poor generalization is really real. Moreover, maybe something to learn from other revolutions humanities have ever undertaken is that any intervention of this caliber has long-lasting consequences for our society and our environment. Some desirable and predictable, some maybe unpredictable and undesirable, like social inequality, the destruction and depletion of natural resources. So being much more mindful about this and trying to anticipate this can go a long way. Thank you for your time and your attention. That's all for me.
All right, guys, welcome back. We hope that you have enjoyed this talk, and we actually already have some quite interesting questions. So, but still, if you want to ask anything else, feel free to just jump in and press on the button questions over there. And you can also vote on your favorite question if you'd like. And now we have Diana with us. Hi, Diana. How are you doing? Thanks for joining us.
Hi.
Hi.
Thanks for having me.
So I heard you have plans for tomorrow. What's that?
I'm actually flying to Portugal on vacation.
Yeah. Well, we hope that you enjoy, and actually we wish we could have been there to welcome you on an event.
Actually, some other time.
another time. Yeah, but well, we always have the SPT 2021 if we manage to do it live. So you're already invited if you want. Actually, also an interesting thing you told us is that you have 3 bachelor degrees, right? So just out of curiosity, what did you study?
I studied mathematics, electrical engineering, computer science, and an economics degree in international business.
Okay, that's quite different, but this connects directly with the thing that you really like to be involved in different kind of study fields. And did you do that in, I guess that takes a long time. Did you do that in 9 years?
No, some were at the same time, overlapping a bit, which turned out my undergrad years into a very intense experience with very, very little sleep. Oh, wow. But it was a very enriching experience, and it turned out that I can use a lot of these methods and knowledge into what then I discovered as machine learning. Which,
wow. Yeah. Wow! Congrats! I mean, that must have been some tough years. Okay, so we're going to jump right into the questions, and I guess you actually apparently inspired a lot of people watching the talk. And the most voted question, or at least the viewers asked us, is: could you recommend a good source for studying and learning deep reinforcement learning? Is there any kind of, let's say, Bible or any kind of the go-to place for it?
That's a very good question. I think the deep reinforcement learning is a very, I guess, still young field in a sense, and whenever we develop something in RL, we try to make it as independent of the functional approximator used on top of that. In a sense that that means that when a new, more suitable functional approximator comes in, like recurrent neural networks and stuff like that, we could pair it up with classical methods. And in terms of RL, I actually have it on my desk. The new edition of the Rich Sutton's book on reinforcement learning is probably the best introduction in this field, and it goes into the classical methods in reinforcement learning, but discusses some challenges and the pairing with the functional approximator and the I guess the theoretical challenges that comes with that.
Yeah, it's actually a very nice book. I started reading it a couple of weeks back already, and I think that the best way also to go through it is actually if you do the exercises and try to experiment some stuff. Also, at least that's from my little experience from that book.
And if you want something more of a course, we do have a course that we're teaching at UCL that David Silver and Hado's lectures are online. Was going to be another like refresher installment coming up, but the video lectures are online. So that's a bit more advanced, but based on the book and notation there, but more. Like at least the second half of the course is more deep RL-ish.
Okay, maybe then after this talk, could you share the link if you have it on hand on the chat? Perfect. So now let's go to more of a, let's say, applicable part of this, and it's a very general question. So it seems that if you are not OpenAI or DeepMind, it's kind of hard to get into reinforcement learning. I guess reinforcement learning in this case in terms of industry and not academia. So why do you think that other companies are not investing as much in this area?
I'm not sure that's necessarily true. I think it's just the full, I guess, problem of reinforcement learning, as I tried to highlight, is a very complex one. And we may not have just yet the solutions to deal with that generality, but there are definitely smaller problems or simpler problems of this this paradigm, like bandits that are used quite often in recommendation systems. I used to work at Microsoft Research, and they've been using this for years in recommender systems and stuff like that, and we use it for Google Play and stuff like that. So it may not be the what you hear, I guess, or what it advertises is, the frontier of what we invent in terms of methods, and those are usually, we test them on games, and they might not be ripe enough to make it into production just yet.
Yeah, but there is other small areas. Actually, I know for a fact that some of, at least one or two of our industrial partners are also looking into RL right now. So if you guys want to try to find out which one it is, they do have their stands, and please go check them out and just give this small intermission. Let's go to a bit more specific question. So typical computational intelligence problems have to battle getting stuck into local maxima and minima in the search space. How does reinforcement learning deal with such kind of issues?
Very good question. I think we're inheriting some of that for the functional approximators that we are using. And I guess there's two sides to this. In terms of theory, if we stick to the formalism of Markov decision process, there's only a unique solution. So we're almost in a convex setting. There's always only one value function, and the methods under mild conditions are guaranteed to converge to that. Now, practically, whenever we migrate away from that theoretical scenario and we use functional approximator, kind of all bets are off. I think that's one of the things that we still need to reconcile, the gap between the scalable methods that we are applying today and the theory that was developed on much smaller application and maybe exact representations.
Thank you so much for such an answer. Then a bit of more of application, I guess, another application question. So can stock market portfolio optimization considered as a reinforcement learning problem?
Yes, it can. I actually did my master thesis on this. Well, a small problem of this modeling American options, which are just derivatives, financial derivatives that you can execute at any point in time at the particular price. So it was a smaller problem, but is just instantiation of how to do that. And it can you can model it for a lot of course, like maximizing I guess outcome, maximizing the potential of a win. You can maximize for risk aversion and stuff like that. So there's plenty of things to be done in that area. But any sequential decision making problem, in principle, can be treated as a reinforcement learning problem.
Thank you so much. I'm guessing we already have time just for one more question, but I think this is actually a very interesting one. So when you have to solve a reinforcement learning problem, let's say aerial navigation, autonomous sailing, etc. Well, in order to solve that, you have to create a simulation environment, which also has some kind of physics engine, right? And do you know whose job it is to specifically develop that simulation environment, or do you think it's the let's say the RL's researcher role in this, and should he have knowledge in this kind of toolkits?
Yes, that has a lot of practicalities to it. As a PhD student, you're playing both of these roles. For us, we're trying to. That's why we're going for games. It's something externally specified that we don't have to put in, and then like neither our biases or what makes our algorithm shine, in a sense, ends up being in there. I think that it's important to separate that, because at the end of the day, we want a solution that is tackling a real problem, is tackling a problem that was externally specified and external environment where we can't really control those conditions.